So welcome to lesson number 6, which is interference and diffraction. These are two very important topics for the Leaving Cert. In the first part of this lesson, 6 part 1, we are going to look at interference. You have some idea what interference is about. You're using your mobile phone and the signal goes bad. There's some kind of bad interference taking place. Interference is about waves coming together, overlapping, merging, and as a result of that, you get some kind of different effect. Now, it's only waves of the same type that will interfere. Obviously, you're not going to have light waves and sound waves interfering. They're completely different types of wave. But even when you're talking about the same kind of wave, you want the waves to have approximately the same wavelength, same amplitude, before you get proper interference. Waves like this that are the same type have approximately the same amplitude, same wavelength, same frequency. We say those waves are coherent. And coherent waves come from coherent sources. So what's my definition of interference? Interference is what results when waves from 2 or more coherent sources overlap and combine to form a new wave. Sometimes that new wave is good. You get a very strong signal on your mobile phone. Sometimes it's bad. The signal drops out. So we're going to look at 2 kinds of interference. We'll start off by looking at constructive interference. So constructive interference. You've got some diagrams in your notes that you're going to draw on. I'm going to take 2 waves. And I'm going to have their starting points in the same place. They're going to have them both starting exactly here. Because they're starting together, I say they're starting in step. Or another way of saying in step is in phase. So my 2 waves are in phase. So everything about my waves is going to be the same. They're going to have the same amplitude, same frequency, same wavelength. So let me take an example of a wave. So here's my wave. You can see what the amplitude is. That's the height of the wave. So from the central position right up to the crest or down to the trough, there's my amplitude A. Now I'm going to take an identical wave, starting in the same place. It's got the same amplitude. They're starting in step. And these 2 waves meet each other in space. And what's going to happen is they're going to merge together. So what happens here is, you see that crest is going to meet that crest. And what do you think is going to happen? You're going to get a much higher crest. That trough will meet that trough. And what do you think is going to happen? You're going to get a much deeper trough. So you end up getting a resultant wave, which I'm going to draw here, of a much higher crest and a much deeper trough. The amplitude will be the combined amplitudes of the 2 waves. So you'd have A plus A giving me twice the amplitude. Constructive interference, sometimes for shorthand I call it CI. That's usually the good stuff in the sense that it'll give you a strong signal. So constructive interference occurs when 2 waves meet each other in step. They're coherent waves. In other words, they're pretty alike. And when they combine, they'll form a much stronger wave. Now, what's the opposite to that? The opposite to that would be what we call destructive interference. Let's have a look at destructive interference. So again, I'll be drawing these diagonals from your notes. So I'm going to start off with a wave as before. So here's my wave. It's got an amplitude A. It's going to meet a very similar wave, but this time the wave is not going to start in the same place. In that second set of diagrams in your notes, just extend that line back a little bit. I'm going to have this wave starting half a wavelength early. You know what half a wavelength is. There's half a wave there. So I'm going to have this wave starting half a wavelength early. Then my wave continues as so. Once again, its amplitude is A. Well, what's going to occur here? You can see here that crest is going to meet that trough. And if they have the same amplitude, they're going to cancel each other completely. What we're looking at in the leading cert is total destructive interference. I sometimes shorten that to DI. I mean, you can also guess partial DI, but we're not going to look at that here. We're just going to look at the total extreme situations. So crest meets trough, trough meets crest, and as a result of that, the waves will completely cancel. So here's my wave here. You might get a little bit of a ripple. Essentially, the wave has disappeared. Your signal has been lost. The overall amplitude here will be 0A, 0 amplitude. What's occurred here? Well, these two waves, that starts there, that starts there. That second one starts half a wavelength, half a lambda, out of step or out of phase. When that occurs, you get destructive interference where the signal disappears. Let me have a look at the definitions. Go back to my notes. These are definitions that I need to learn. There's no asterisk beside them. So what's my definition for constructive interference? Well, my definition is when waves from two sources meet and the amplitude of the resulting wave is greater than the amplitude of each of the individual waves, then we're talking about constructive interference. And what about the opposite one, destructive interference? When waves from two sources meet and the amplitude of the resulting wave is less than the amplitudes of each of the individual waves, then we're talking about destructive interference. Now, I need to know the condition for constructive interference and the condition for destructive interference, or DI. So what's my condition for CI? Well, my condition for CI is the waves have to be in step. But actually, what would happen if they started? See this wave here? This wave started a full wavelength behind. Well, that's the same situation, isn't it? So if it was one wavelength at a step, you would still get CI, wouldn't you? Because crest would still meet crest and trough would still meet trough. So what we would say is the condition for CI, constructive interference, is that the waves are in phase, or I suppose another way of saying that is they are zero wavelengths out of phase. That's another way of saying it. Or one wavelength, or two wavelengths, and so on, out of phase. In other words, they are a whole number of wavelengths out of step. That will give you CI. And what's the condition for destructive interference? Well, for DI, the condition for DI Well, what I showed you here, it was half a wavelength at a step. So we're talking about half a wavelength at a step. But you could also have a full wave back to the left here as well. That would be 1.5 wavelengths at a step. So 3 halves lambda at a step. 5 halves lambda at a step. And so on. That would give you destructive interference. This is the one I think they'll ask you mainly in the exam. They'll sometimes say, what is the minimum condition for DI? And the minimum condition is they are half a wavelength out of phase. And that's the one where they will ask most of their problems. Finally, one more definition I need to look at. It's what we talked about earlier. It's a definition for coherent sources. So coherent sources give rise to waves of the same frequency and amplitude that are emitted in phase or step. Let's have a look at example 1. This is actually a very interesting example. We've got radio waves of frequency 30 kilohertz. See that kilo, that's a prefix. Are received at a location of 1,500 kilometers from a transmitter. So here's my transmitter. The radio reception temporarily fades due to DI, destructive interference, between the waves traveling parallel to the ground. The waves are going to travel along the ground to the receiver. And the waves reflected from a layer high up in the atmosphere called the ionosphere. You might say to yourself, we've never done the ionosphere, but it doesn't matter. We're just trying to make the question interesting. The ionosphere is a band of particles high up in the Earth's atmosphere that acts like a mirror to the radio waves. So what they want you to do, first of all, in part A, is to calculate the wavelength of the radio waves. First of all, you might think a radio wave is a sound wave, but it's not. It's actually an electromagnetic wave that travels at the speed of light. So we're going to use the speed of light, and you know where to get the speed of light from. You go to your table book, page 46, 47. They're the middle pages, always open in front of you. And the speed of light there, c, is giving us that value there, which you'll write as 3 by 10 to the power of 8 meters per second. So let's have a look at the question. So here's my question again being drawn. So I have a transmitter here, and it's going to emit these radio waves. You can't see them. They will travel along the ground like this to the receiver. The receiver would be you, for example, with your mobile phone or your radio or television, whatever you're using. There's another way they can get from T to O, and that's by bouncing off the ionosphere, that mirror in the sky. So they can go up here, hit the mirror in the sky, and come back down again. The laws of reflection will be obeyed here. The law of reflection will be that the angle of incidence I here is equal to the angle of reflection. And basically that means you're talking about here two right-angled, congruent triangles. They are the same. You're told that the distance from transmitter to receiver, this distance here, that is equal to 1,500 kilometers. So this is a challenging question. Because these two right-angle triangles are congruent, I suppose I can say that bottom side there is 750 kilometers, and this one here is also 750 kilometers. Okay, so what's the first thing they're asking me to do? The first thing they're asking me to do is to find the wavelength of the radio waves. Well, I'm going to use the wave equation here. And because we're talking about light, radio waves is the light wave that you can't see, I'm going to use C is equal to F lambda. I'm going to take the value of C from my table book and round it off to one decimal place. And I get C is 3 by 10 to the power of 8 meters per second. They tell me in this question that the frequency, F, of the radio waves is 30 kilohertz. You see that kilo there? That kilo there is a prefix. And most times, I'm not saying all times, because sometimes you're going to have kilograms and you don't change the kilo into 10 to the power of 3. But here, the units of frequency are hertz. So I've got to change the kilo into its power of 3. Well, it's 10 to the power of 3, or if you like, 1,000. So you can write down the frequency is 30,000 hertz. So always get into the habit of treating your units. Set your units out properly and make sure they're all written correctly. I'm looking for lambda. So I'm going to manipulate that formula. So lambda is equal to C divided by F. So C is 3 by 10 to the power of 8. And F is 30,000 hertz. So put that into your calculator. So press the fraction button. Top 3 by 10 to the power of X divided by 30,000 on the bottom equals, and I get 10,000 meters. That 10,000 meters, that's 10 kilometers or 10K. I might decide to put all my units in kilometers, which is okay. So when you do all your calculations, your answers will be in kilometers. You can change everything to meters if you want, but it doesn't matter as long as you know what you're doing. So basically, they gave me kilometers here, so I'll turn that into 10 kilometers. That's the wavelength of my radio waves. That's a huge wavelength, 10K. That's why radio waves are so useful. Their waves can leap over mountains and around the curvature of the earth. That's why they're so useful in telecommunications. The wavelength of my radio waves is 10K. Right, let's go back to my question in our notes. So what's the second part, part B? They're asking me the question. The question they're asking me is, what is the minimum distance? You see that word minimum? That's what I talked about earlier when I was talking about the condition for DI. And I said the condition for DI is that the waves are half a wavelength out of phase, 1.5. When we talk about the minimum, we're talking about a half a wavelength out of phase. That the reflected wave should travel for DI to occur at the receiver. Right, so what I'm saying here is this. I'm being told that DI occurs right here at the receiver. Well, you've got two sets of waves coming together. You have the one traveling along the ground and the one bouncing off the mirror in the sky, interfering at that point. Now, obviously, the one that bounced off the mirror in the sky, that's got further to go. The question is, what is the minimum extra distance it went in order for DI to occur there? What's the minimum condition for destructive interference? It is the waves are half a wavelength out of phase. That is the condition for DI. The minimum condition is half a wavelength out of step. Now, what is half a wavelength? Well, half a wavelength is, a full wavelength is 10 kilometers. So half a wavelength is 5 kilometers. Do you know what we're saying? We're saying that this wave that bounced off the ionosphere traveled an extra 5 kilometers, which is an extra half a wavelength. So when it joined with this one along the ground, they were out of step by half a wavelength, and so DI occurred, destructive interference occurred. It's a difficult little concept to get, so I hope you understood what I was talking about. What's the overall answer then? The question is, how far did that one travel altogether? Well, this one traveled an extra 5 kilometers. This one traveled 1,500 kilometers. That means the one that bounced off the mirror in the sky traveled a distance of 1,505 kilometers is your answer. What's another distance it could have traveled so that DI occurred? Well, what about 1.5 wavelengths? 1.5 wavelengths would be 10 plus 5, 15 kilometers. So it could have traveled 1,515 kilometers, and DI would also have occurred. But this one here is the minimum, and that's the one they will probably almost always ask. Right, let's go back to the rest of my question. So the next part of my question is, the layer at which the waves are reflected is at a height h above the ground. Calculate the minimum height of this layer for DI to occur at the receiver. Well, actually, the physics is more or less finished now. We just have some very simple junior cert maths to do. So if I look at this right angle triangle on the left, I know that the total distance here is 1,505 kilometers. The two triangles are congruent, which means that side is equal to that side. So if I divide the 1,505 by 2, I'm going to get 752.5 kilometers. So you're just talking about using Pythagoras. I want to find the height h there. So I can say very clearly that h squared plus 750 squared is equal to the hypotenuse squared, 752.5 squared. I left everything in kilometers, which means my height will be in kilometers. You could have changed everything to meters, but you're just dealing with much bigger numbers. So let me do that calculation for part C. So for part C, I've got h squared plus 750 squared is equal to 752.5 squared. We'll solve that first of all for h squared. Jump the 750 squared across. And then h will be the square root of all of that. You know, in physics, I like to do a lot of my calculations in one go. Instead of working out all these numbers separately and rounding them off, I like to try and do them in one go like this. So I'm going to put that into my calculator. So I've got the square root of 752.5 squared minus 750 squared. That's equal to 61.3 kilometers. So that's the height of the ionosphere in this particular question. Finally, let's look at some real-life applications of interference. I've got two real-life applications here. One involves soap bubbles and petrol films. So you've got maybe some petrol mixing with water lying on the road. You can see colors produced by interference. So basically all that's happening here, let's say you've got a layer of petrol that lies on top of water. A light comes in and shines on it. Well, some of the light will be reflected off the water. Some of the light will be refracted, pass through, and be reflected off the petrol. And now you've got two waves coming through, and these two waves will interfere, and some kind of colour will be formed. That's one application. Another application is noise reduction by interference. By destructive interference, should I say. Destructive interference isn't always bad. Obviously, if you've got a mobile signal and it disappears because of DI, that's bad. But DI can have some good uses as well. Let me talk about one of those good uses. So let's say, for example, I'm at the airport and I'm going to involve DI with noise reduction. So when you walk through the airport, you've got these giant air conditioners up in the ceiling. They're there, otherwise the airport will become very humid and slippy and very dangerous. But these air conditioners high up in the airport, they make a horrendous noise. So walking through the airport would become a very difficult experience. Let's say, for example, that's the waveform of the noise coming out of those air conditioners. If they smash into your eardrums, they would do your head in. Well, we could do something very clever. We can pass these particular waveforms, these sounds from the air conditioners, into a microphone. The microphone will pass them into a bit of electronics and turn that waveform upside down. So if I was to draw the upside down picture of that waveform, I'd get something like this. I won't be completely accurate. So basically, I produce that upside down waveform. Then I feed this bottom waveform into loudspeakers, and these loudspeakers will be at ear level as people walk through the airport. What you have here is this situation. You're now going to have that waveform, that sound coming from the air conditioners, which is not very nice. And then you've got this waveform coming out of loudspeakers at head level, the upside down picture of that sound. They come together. And what you can see there is everywhere I've got a high point, it's matched by a low point by a high point. And what you end up getting is destructive interference. You might get a little bit of a ripple, but basically you get hardly any sound at all. So we're actually using destructive interference for a very good purpose, for noise reduction. We also have it in cars. If you've got a car with a very loud engine, then you can do the same thing. You can take its waveform, turn it upside down, feed that into a loudspeaker behind the head of the driver. These two forms come together and you're driving along in total silence. So that's a very good application of destructive interference. Now, that's just about it. Everything to do with interference. And now it's over to you. There are some questions at the end of this chapter. And I want you to do these questions before moving on. There's some nice questions, actually. They're quite challenging. So there's a lot of different situations shown here involving loudspeakers. They require a little bit of thought. They're nice and easy. They involve very simple maths. They involve the principle that the minimum distance for DI is half a wavelength. So you'll be using quite a lot of that. So what I want you to do questions 1, 2, 3, and 4. That question 4 is very like the one that I just did in this particular lesson. Okay, that's the end of the lesson. Thank you.